Hello, I'm Samuel Oshiro, and this is my review on our business application for Family Search, Family Search Heritage Vault 2.0 initiative. I'll walk through the entire business requirements and show how we've designed our Linux environments to solve the problems that we face that we are trying these problems. The focus is on automation, administration, storage, security, and networking, and it hopes to reduce human error, protect our record, and keep our system reliable for our global usage. So we are going to deal with the heritage, multiple to the business needs. Then move on to the core system requirements, our solution, and finally the configurations and the outcomes at the end. So the initial requirements we have is Heritage Vault 2.0. Family Search must serve millions of members, researchers, and genealogists who need to access records at the same time, which means concurrency and uptime are of utmost importance. Since these archives contain personal and sensitive information, our system must strictly protect confidentiality and prevent unauthorized changes to records. Since we know the data itself is irreplaceable, the storage itself must be redundant and recoverable even after hardware failure. We cannot allow disruptions or even natural causes to have us looking for data after they have been destroyed in one place. Finally, as we grow and scale, we must implement search algorithms for indexing and to ensure retrieval stays fast and users can use the system efficiently. So in all of these things that we deal with, we know that we require high volume concurrent access, robust privacy and data protection, redundancy and recover, recoverability on storage, and lastly, fast and scalable search and retrieval. All of these must be baked into whatever system that we build. With that in mind, let's discuss how we decide to automate the entire system. Automation is the first key here because the main goal is to reduce human error and make sure our system is consistent when dealing with routine tasks. So we we've ensured that routine tasks are automated using Bash script and scheduled with Scrum or Scrum jobs. We now use a unified script to handle multiple modes, such as updates, backup, and health checks, so our administrators can have a single and predictable workflow and predictable results as well. For each automated that job, we log the activity and we check exit codes. This ensures failures are visible quickly instead of leaving silent problems that might impact our users. For example, when a when we run a backup, if there is a failure, a hardware failure, we need we are going to get an error code that's going to show up and tell us, okay, there is a failure somewhere. So we know what records have been backed up and what records still need to be backed up. In a system with global traffic, predictable and transparent maintenance must be supported because this also in turn supports uptime and keep our operations aligned with our overall policy. Next, let's discuss administrative control, given that administrators will run the system. So administrative access is going to be is tightly controlled if was done to lower the risk of misuse and mistakes. SSH access for privileged users relies on key-based authentication, while password-based SSH and direct root logins are absolutely disabled. No one within the system can log in as root, which will help prevent brute force attack and shared root credential among administrators, which then can be misused in case an employee leaves the company. And we make sure that we have all passwords can be easily deleted without having to change or root the root password whenever an employee leaves or is promoted out of the current team. User accounts are created and removed through standard lifecycle scripts that enforce consistent scope assignments and privilege limits. Authentication events and pseudo activity are forwarded to the central system log host. This provides a single reliable audit trail which supports oversight, incident investigation, and accountability. Given that everything that we do is logged, it ensures there is always a trail for whenever something goes wrong and we can go back to check what happens. So to recap, we have SSH key only login for administrators, password and access based um, access for SSH is blocked. Direct source login is also blocked, which will mitigate risk. Standardized onboarding and offboarding are scripted for user management to ensure consistency, especially when it comes to group membership and privilege levels. This is in hopes to reduce risk configurations. So when a user is created using a script and assigned to a team, they have only the privileges and assigned to a group, they have only privileges assigned to that group. And also we have our RSS logs for centralized logging, performance authentication and pseudo activities to central host. So we have comprehensive audit trails and accountability. So moving on, for our storage and kernel decision focuses on scaling performance while preserving data integrity. Kernel parameters in etc/system.conf is can be tuned to reduce swapping and handle heavy input and output during indexing and search, which will help to keep our response time stable. Our hope is to ensure no serious lag or latency across usage. Our logical volume manager separates archived data, index data, and logs into their own logical volumes. And this can be expanded online so our storage can grow without major redesigns. Our hope is to make sure that scalability can happen with just as simple, with as little hassle as possible. We are also using return. We've chosen to use return for the read and write capability and fast review time compared to the other the compared to many Paris-based systems based arrays, which is important in a system that's always active. Since we are ensuring consistent uptime, RAT10 is best to be used for this. We're also using XFS as a file system because it's well suited for large files and huge directories, which makes it a practical choice for our large database. So that is hope will give us stability and performance with very large files. In terms of security measures that we've taken, we have SE Linux, LC Linux enforcing mode, which is implemented with targeted policies to confine public-facing services and limit the impact of potential application compromises. So the public-facing services can only read and modify files within their approved scope. So users can only deal with their files and their files alone, not interact with other users' files, which will reduce the impact of application level compromise from bad actors. Our backup and exports are encrypted using GNU-PG before leaving production servers, which will help protect the data in transit and in our offsite storage locations. We also make sure that when it comes to our patches, they are applied promptly in scheduled windows after being tested in our staging environment. So our security issues are addressed without causing unnecessary outages. Then finally, we deal with quarterly baseline scan using open CAPs or CIS-based checks that will help identify outdated packages, misconfigurations, and privilege drifts before they become serious vulnerabilities. Since we are going to keep our eye on all our packages and make sure that to ensure that whenever any of them becomes a security threat, we can easily update or even remove them or swap them for something else that will work better for us. For networking architecture, we use a default deny firewall rule, and the idea is to limit exposure while keeping our services reachable and resilient. Our firewall only allows specific service ports that are required. SSH access is restricted to only VPN subnet rather than the entire through the open internet. So users must use our VPN subnet to access it. The open network internet communication are not allowed. We also have network segmentation using VLAN for isolation. So we isolate public API traffic from indexing and storage network as well. That way, a problem in one segment does not automatically endanger others. And then finally, we use bonded links for failover. So link bonding on critical servers ensures redundancy and stable throughput, which helps to maintain our service continuity despite link failures. Our integrated architecture. So this is a summary of everything that we've done. We automated and predictive. We have automated for predictable maintenance. We have centralized and control administration. We have tuned our kernel and make sure storage is resilient. We have used a military security control, and finally, we have segmented for fault tolerant networking. And here are the references that we have used for this presentation. Anicas 2021 digital mission, and so on. And that brings me to the end of this presentation.